Welcome back to Calculus 1. This is part 2 of our lecture on limits at infinity. In part 1, we introduced a new algebraic trick for dealing with indeterminate forms of the type infinity over infinity, and we'll look at some more examples with those indeterminate forms. All right, now this is a good example for you to try. Typically, after going through at least one example with my students in class on limits at infinity, like our previous example 1, I would give this as a kind of a follow-up example. I'd like you to pause the video and give this an attempt. This one is simultaneously a little tricky and simple, depending on how comfortable you are with some previous topics from pre-calculus. So before you start, just to give some hints before you make an attempt, we're going to want to look for, within this expression, what the largest term is. So either the largest term as x approaches infinity, there could be one largest term, or maybe there could be a different largest term as x approaches negative infinity. Really think about it. Give this an attempt. We'll check in about maybe 3 or 4 minutes. All right, welcome back. Hopefully you made an attempt. Now, I'll probably say the limit as x approaches positive infinity here is the one that's a little easier and more straightforward, not as tricky for students compared to the limit as x approaches negative infinity here, which is tricky, but not difficult. So let's go through the limit as x approaches infinity. What we're going to recall first is the graph of e to the x, which we kind of stated was important from part 1. That's one of your basic functions that has a limit at infinity. But notice here, e to the x only has a limit that exists towards negative infinity. As x approaches negative infinity, e to the x approaches the real number 0. As x approaches positive infinity, e to the x approaches infinity. It just gets really big. It grows exponentially. All right, now, right now, we're going to look at the limit as x approaches positive infinity. And our function here involves basically 2 types of quantities. We have the exponential quantities within the numerator and denominator, e to the x, and then just the numbers, 7 and 2. So what we're going to keep in mind here is as x approaches positive infinity, the largest term is going to be the exponential function, e to the x. All right, eventually e to the x greatly outpaces constant functions, and e to the x grows incredibly fast. So e to the x will be bigger than 7, and e to the x will be bigger than 2 rather quickly. All right, so our largest term is e to the x. We're going to divide everything by e to the x, all terms within the numerator, and then all terms within the denominator. All right, just make sure you're comfortable canceling out. And notice what we're left with, 7 over e to the x within the numerator, and then 2 over e to the x within the denominator. Those are not reciprocal powers, but they are reciprocals nonetheless. 7 divided by e to the x is getting smaller because the denominator, e to the x, is getting bigger. So here, if we finish evaluating, taking the limit as x approaches infinity, we get here that the whole limit for the function approaches 1. Again, it's the reciprocals of e to the x, 7 over e to the x and 2 over e to the x. They both approach 0 as x approaches positive infinity. So with minimal effort, seems very similar to example 1. We identified the largest term, e to the x, divided everything by that largest term, and then we get our reciprocal limits. But now, not reciprocals of powers of x, but reciprocals involving exponential functions. Exponential functions get big as x approaches infinity. At least e to the x does. All right, why should the limit as x approaches negative infinity be any different? Well, before we even advance to the next screen, take a look at the top there. E to the x only gets big in one direction. E to the x gets big as x approaches positive infinity. As x approaches negative infinity, e to the x gets really small. And that's going to make the difference here, why this function has a different limit towards negative infinity than it does for a limit towards positive infinity. All right, so let's take a look at the second part for this. This one was probably the trickier one, but it's almost always somewhat easier for students. All right, and what we have to be clear on is now as x is approaching negative infinity, there is a different largest term. So make sure you realize, look at the graph above, as x approaches negative infinity, e to the x is getting small towards 0. And what that means, as x approaches negative infinity, 7 and 2 are bigger than e to the x as x approaches negative infinity. So our largest term for this limit at infinity, as x approaches negative infinity, the largest term is not e to the x, the largest term is just a number. And actually, we don't have to do anything here. We don't have to divide by a constant number, since the exponential function e to the x approaches 0 as x approaches negative infinity. So kind of written in disguise here, we already have quantities that get small, but they're not written as reciprocals. You have to be comfortable with that. Exponential functions exhibit two different types of behavior depending on if x is approaching infinity or if x is approaching negative infinity. So here, all we have to recognize is that e to the x within the numerator and denominator are both getting small towards 0 as x approaches negative infinity. So we get here, the limit as x approaches negative infinity is 7/2. The exponential functions e to the x both approach 0, leaving you with the numerator approaching 7, the denominator approaching 2. So the whole function, or y value, approaches 7/2. Okay, this is a good example. It's not complicated. Notice the work is very minimal here, but it's a good question since it's kind of exhibiting different limits at infinity towards positive and negative infinity. Now, each of these limits, we have here the limit as x approaches positive infinity, the limit was 1, and as x approaches negative infinity, the limit was 7/2. What this tells us is this function has horizontal asymptotes, y equals 1 and y equals 7/2 as x goes very far to the right and left. We have different horizontal asymptotes in different directions, which is completely fine. All right, now when you're ready, we're going to take a look at a follow-up example, example 3. It's probably one of the more complicated limit questions that we've encountered. And just again, to thoroughly prepare you for what occurs within the calculus sequence, we sometimes have to take a look at fairly difficult questions. All right, now before we jump into it, there's going to be an important property that I always like to review. And depending on your background, how comfortable you are with algebra or pre-calculus, you might either know this next review thing, or it might be completely foreign. So I had to kind of assume with our online recorded lecture that I can cover everything. So let's go take a look at a review topic from algebra in hopefully complete detail before getting into the next example. All right, now what I would like you to do, just to see how well you understand some of your topics from algebra, what does the square root of x squared simplify to? I'm going to do a long dramatic pause. Really think about that. If needed, pause the video, take a look at several cases. Think of x maybe as a positive number. Think of x as maybe 0. Think of x maybe as a negative number. see what you are led to. We'll check in maybe 10 seconds. All right, ready for the answer? This is going to test how well you know algebra. This correctly simplifies, for all cases, the absolute value of x. Now, why is that? Usually, we're very informal, and we say a square root of something squared cancels. Well, that's not always true. We're being a little informal. A lot of times, the quantities involved are positive. So a square root of a positive number squared cancels to that positive number. There's a problem with negatives. So let's take a look at two concrete examples to show you why we have to be careful with what this simplifies to. So let's suppose we have the number 2, which we're going to square 2 and then take the square root. So take a look at the order of operations. 2 squared is 4. Then the square root of 4 is 2. And we get the same number that we started with. In other words, we started with 2, squaring and square rooting canceled, giving us the number we started with, 2. Now, cancellation does not occur. In other words, we don't get the same number as we started with if x is negative. Let's go with x equals -2. Follow the order of operations, work within the innermost part, kind of the parentheses. -2 squared, +4, square root of 4 is 2. The number we started with was -2. Here, squaring and then square rooting -2 does not cancel out and give you the number you started with, -2. It cancels to +2, which was the absolute value of the number we started with. Okay, now just to be clear, we will say the square root of something squared cancels, provided that something is positive. Here, in the questions we'll be looking at the level of calculus, it's a little trickier. We have to be careful. The square root of something squared does not cancel to that something when that something is negative. Now let's take a look at the kind of two versions I like that are a little bit better. There's nothing wrong with that statement above involving absolute value. It is mathematically correct, but I find it makes some of the problems a little bit harder to deal with. So let's take a look at two cases, that cancellation rule when x is positive, and that same cancellation rule when x is negative. We'll use that idea when we go through the next example. Okay, so we have two versions for this cancellation. The first version, when x is positive, is direct cancellation. The square root of something squared, the square root of x squared cancels to x when x is positive. That's going to be relevant when we're doing a limit here, a limit at infinity as x approaches positive infinity. Like the previous example, example 2 that we looked at a limit as x approaches positive and negative infinity. Now we have to use this other cancellation property when x is negative. The square root of x squared cancels not to x, since x can be negative. This will cancel to -x. And the notation looks confusing, but keep in mind here, x is assumed to be a negative number, and what we have on that right-hand side is a negative of a negative number, which is positive. All right, so just make sure you're comfortable where that negative comes from. This is an equivalent way to write that absolute value statement above, which the two versions down here, the version for when x is positive and then the version for when x is negative, will be a little easier to use, I found for my students when we go through the next example. So when you're ready, we're going to advance to the next example. Pause just to make sure you fully get this. When you're ready, unpause and we'll take a look at the next example. All right, and with that, let's get to the next example, example 3. This one's going to be fairly complicated. I will try to take my time going through this with you, since again, we're not live. We don't have that face-to-face interaction that I find is crucial in my calculus courses. So I have to kind of rely on doing the most I can with the recording here. All right, so I'd like you to make an attempt at this. Definitely make sure you understand that square root property with cancellation. It's going to make all the difference here when looking at a limit as x approaches positive infinity or as x approaches negative infinity. Now this one is a little trickier. You have to identify what the largest term is, but it's not hard. But I'd like you to make an attempt, and if you find you're kind of stuck getting started, just unpause and we'll go through it, but I'll give you maybe a minute to see if you can make some progress with it. All right, now let's go through part of this together. The first part, in case you were stuck, is identifying what the largest term is. All right, so this is kind of like end behavior for a polynomial. We'd like to say 9x squared is bigger than 1 when x becomes large, which it is. But notice all those quantities, 9x squared plus 1, are within that square root. So we say the largest term is then the square root of the largest term inside. All right, so our largest term here simplifies to square root of 9x squared. Now this is where you have to be careful. Don't be careless. We are letting, within these two different limits, x approach a positive number, positive infinity, or as x approaches negative infinity. So x is going to be thought of as a positive or negative number. We have to be careful with the cancellation here. Now when x is positive, that'll be relevant for the limit as x approaches positive infinity. Square root of x squared does cancel to x. So overall, the square root of 9x squared would cancel to 3x. But when x is negative, as x approaches negative infinity, the square root of 9x squared simplifies to negative 3x. All right, just make sure you're comfortable with that. I've had those results summarized there on the right. Notice, depending on the direction, we have a different sign for what it behaves like. All right, let's take a look at the next part. If you were stuck identifying the largest term, maybe pause to make a second attempt here. The largest term is x. Now for the numerator, we would say the largest term is 3x. It's what the numerator behaves like for large values of x. The denominator is just x, but that factor of 3 doesn't really make that much of a difference. Think of 3 million versus 1 million. They're both fairly big. That factor of 3 doesn't really make a huge difference. So for simplification, we'll just use the largest term as just x. That makes the algebra a little bit easier. So now that we have our largest term, divide everything in the numerator, the single square root, and divide everything in the denominator by x. We'll check in a little bit. Either your algebra skills are top-notch and you get through this effortlessly, or your algebra skills are not top-notch, which for most students is the case. Algebra is the deciding factor for how well a student does usually within the calculus courses. We'll check in about a minute. All right, let's go through this limit as x approaches positive infinity. We're going to do some of the algebraic simplifications using that previously mentioned square root property, that cancellation property. And we'll kind of take a look at the work needed for both parts here as x approaches positive infinity and as x approaches negative infinity. Okay, so we're going to start off dividing the numerator by x and then divide everything in the denominator by x, since we're advocating for an indeterminate form of type infinity over infinity, which we have here. our algebraic trick is dividing by the largest term. So we'll divide everything, all terms, by x. Now the denominators, that's easy to simplify. The numerator, the square root of 9x squared plus 1, all over x, that's where the work is going to be. So let's do that work down here on the bottom. We'll kind of do this up to a point where there will be a difference that we'll make use of between the limit towards positive infinity, and then we'll show you where the difference in this simplification occurs for the limit as x approaches negative infinity. All right, now recall the reason that we divide by the largest term. Our goal is we're trying to mathematically rewrite this function with reciprocal powers in it. All right, so let's think how we can quickly get reciprocal powers. There are several equivalent mathematical and algebraic ways to do this, but this I found in my years of teaching is the simplest approach that students prefer. Well, to quickly get a reciprocal inside the square root, let's factor x squared out within the radical. All right, since 1 has no x squared factors in it, we can think by factoring x squared out, we're left with 1 over x squared. Now, that's a little uncertain for you. Just distribute x squared back in through the parentheses. Check that it correctly simplifies to 9x squared plus 1. But notice that x squared is factored out within the square root. All right, now we're going to apply properties of square roots. We're going to take the square root of x squared, and then take the square root of 9 plus 1 over x squared. And this is where we have to be careful, because we're trying to cancel the square root of something squared. Now, fortunately, for the limit as x approaches positive infinity, we can cancel carelessly. In the case when x is positive, the square root of x squared just cancels to x. And notice what happens. The square root of x squared simplifies to x. That's the upper arrow or upper path there for the simplification. The case when x is positive, since x is approaching positive infinity here. And notice x divided by x cancels out, leaving us with that kind of overall bigger numerator within that complex fraction, simplifying to the square root of 9 plus 1 over x squared. We're going to put that back up in the numerator there, kind of in the middle of the page momentarily. Now, while we're at it, this is kind of most of the work for the second part, the limit as x approaches negative infinity. And notice the difference where the algebraic differences occur. It's in simplifying the square root of x squared. That's the only difference here. Now, as x approaches negative infinity, when x is negative, the square root of x squared doesn't cancel to x. It properly cancels to negative x. Now we get an overall similar end result, but now that extra negative gives us this whole expression, this fraction, simplifying to negative the square root of 9 plus 1 over x squared. All right, so pause to make sure you thoroughly get that. And when you're ready, we'll use that upper path there, the case when x approaches positive infinity, to finish this problem. All right, so let's put that in. That's going to be the simplification for the numerator. Notice the numerator of that fraction, while itself is a fraction, that's what we just simplified to the square root of 9 plus 1 over x squared. All right, so we'll plug that result in. The denominator here simplifies to 1 plus 4 over x. And now we have reciprocal powers within the numerator and denominator. As x approaches infinity, those reciprocals approach 0, giving us here the limit approaching square root of 9 over 1. So we get here our function approaches 3 as x approaches positive infinity. Right, and this one was definitely algebraically involved, gets a little technical due to that square root property about properly canceling the square root of x squared. All right, now this is most of the work for the next part, the limit as x approaches negative infinity. And the only difference is kind of right at the end there where we go down that arrow going down the other path for simplifying for the case when x is negative, as x approaches negative infinity. So see if with this work, before we advance to go through that second part, maybe this will be enough of a hint to get you through trying the limit as x approaches negative infinity for this example. Give yourself maybe 1 or 2 minutes. We'll check in. I'll keep this work up as you maybe go through that. All right, when you're ready, let's take a look at the second example. The only difference occurs right at the end there where the arrows split the simplification. We're going to take the bottom path or the lower path, giving us that negative, the square root of 9 plus 1 over x squared. All right, let's go through the second part. Again, we're going to identify our largest terms. Now, the square root of 9x squared will simplify correctly to negative 3x. So we'll say our numerator behaves like negative 3x as x approaches negative infinity. Our denominator still behaves like x. Now that factor of negative 3 doesn't really make a difference. We'll just use the kind of part containing x, what the true largest term is. Within your science courses, you might call that the largest term by order of magnitude. So we'll divide everything, again, by x. Same as before. And now we're left simplifying the square root of 9x squared plus 1, all divided by x. The only difference is what that simplifies to. And now we're going to use that the square root of x squared cancels to negative x. All right, same work as going through the previous part. The only difference is right there. The square root of x squared cancels to negative x. And that's because x is now assumed to be negative since we're letting x approach negative infinity. And then that's the only difference. It simplifies similarly. Now we have reciprocals, but notice that extra negative makes all the difference. This limit, as x approaches negative infinity, is negative 3. All right, now hopefully that made sense. Again, I tried to take my time. Definitely go back and thoroughly understand that square root property so you can really see why and where this extra negative comes from. It's not made up, but it builds from those basic algebra principles. All right, and that's basically it for this 2-part lecture on limits at infinity. Now let's think why we're covering that. We'll use our standard long-term goal. We're using a lot of topics as we learn them to eventually all come together to curve sketching. That's our kind of previously mentioned long-term goal. So what do limits at infinity tell us? We interpret them as horizontal asymptotes. So this function has a horizontal asymptote, y equals 3, as x approaches positive infinity. And it has a horizontal asymptote, y equals negative 3, as x approaches negative infinity. That's what we're going to use limits at infinity for within our course usually, determining asymptotes and end behavior for complicated functions. Also, just to close, limits at infinity introduce the second most standard type of indeterminate form, infinity over infinity, which is also an indeterminate form. Think back to our lecture on the limit laws. We were getting you to think that whenever you encounter an indeterminate form of any type, there's some sort of algebraic trick involved. For infinity over infinity, that indeterminate form, our algebraic trick is dividing by the largest term, dividing everything within the numerator and denominator by whatever the largest term is. The largest term is usually x to a power or an exponential function.